Good morning, welcome to the class. Today we are going to discuss an important topic in advanced data analytics, how cube technology can be used to process complex queries. We will particularly focus on two special types of cubes, sampling cubes and ranking cubes. These structures help us handle large data sets more efficiently and enable faster, smarter decision making in business intelligence, reporting and data science. First, let us understand what cubes are. In data analytics, a cube is simply a multidimensional array of data. You can imagine it as an extension of a spreadsheet, but instead of just rows and columns, it can multiple dimensions like time, product, or location. This structure is heavily used in OLAP or online analytical processing. Cubes are crucial for applications such as businesses, intelligence, dashboards, financial reporting system, and data visualization tools. Why do we even want advanced queries? Well, in modern data systems, we deal with massive datasets. Queries like what is approximate trend in sales or which product or top performance look at both speed and accuracy. Without technology, answering such queries would involve scanning huge amounts of data, leading to high computational cost and slow response time. Let's move on to sampling cubes. These are special data structures that allow us to approximate query answers by working with only a sample of the data instead of the full data set. The main idea is that sometimes we don't need the exact answer. A close estimate is enough. For example, if we want to see a sales trend, we can use a sample subset of transactions to get a good picture without analyzing every single record. Sampling cubes bring several benefits. They greatly improve efficiency by cutting down computation time. They are scalable, meaning they can easily be applied in distributed systems. They are also flexible as they can help with the trend detection, anomaly identification, and more. For instance, in e-commerce companies often estimate product demand based on sampled customer data, which allows for faster decision making. The real value of sampling lies in the handling very large datasets efficiently. Instead of processing millions of records, we process a smaller representative subset. This reduces the computational cost and improves the query response time. Of course, there are trade-offs. We can sacrifice a bit of accuracy for much greater speed. So we must balance efficiency and precision depending on the application. Now there are several techniques for sampling. The three most common ones are random sampling, stratified sampling, and reservoir sampling. Each has its own use cases and strengths, and we explore them one by one. In random sampling, every data point has an equal chance of being selected. It works well when the dataset is uniform and when we only need a quick estimate. The average is that it is simple and scalable. However, the drawback is that it may fail to represent important subgroups, especially when the data distribution is skewed. To perform random sampling, we assign unique identifiers to data points and then use the random section algorithm to pick samples. This ensures fairness and reduce bias. For example, if we randomly select 5% of customer face records, we can analyze those to estimate larger scale records. Stratified sampling improves on random sampling by divided data into subgroups called strata. Then, sampling from each subgroup. This ensures that all important groups are represented. For example, in a dataset with customer age group, we take samples proportional from each age group. This makes the estimate more accurate, especially when the dataset is diverse. The process starts with identifying the strata like products, categories, or age groups. Then we divide the datasets accordingly and select a proportional sample from each strata. A common example is healthcare data. A patient might be grouped by age before sampling. This avoids bias and ensures accuracy. Reservoir sampling is designed for streaming data where the dataset size is unknown or too large to fit in memory. It is particularly useful for real-time systems. The key advantage is that It gives a fair representation of data over time. Drawback is that it can be computationally intensive. Here is how it works. We maintain a fixed size reservoir, say case samples as the name data points arrive. We decide randomly whether to replace an existing element or in a reservoir. The probability decreases as more data flows in. For example, social media platform can use this to monitor user activity trends without storing all the data. Let's quickly compare the techniques. Random sampling is simple and fast, but may miss important subgroups. Stratified sampling is more accurate for diverse datasets, but requires prior knowledge of data distribution. Reservoir sampling works best for streams, but it is slightly more complex. So the right technique depends on the nature of data and the query needs. Now let's move on to the ranking cubes. Like these cubes are designed to pre-compute rankings based on dimensions or measures. For example, instead of scanning through millions of records to find the top 10 products, ranking cube will already have those pre-computed, making retrieval almost instant. Ranking cubes work by pre-computing ranking orders for specific dimensions like region or product category. Then, when a query comes in, the cube dynamically filters and returns results instantly. For example, if you ask what is the highest rated item in the electronics this month, the cube can fetch the direct from stored rankings. Structure includes three main formats: dimensions, measures, and the top key results. Dimensions or attributes like time or product, measures of values like sales or views, and the top key stores the pre-compute highest results such as the top 10 best-selling items in each category. These key techniques are used in ranking cubes. First, pre-computation, which stores top key results during the cube construction. Second, partitioning, it splits the cube into smaller, manageable sections for analysis. And the third, approximation, wrap sampling is used to estimate ranking, reducing computation costs. In pre-computation, the cube stores top key results upfront. This makes query response extremely fast. However, the downside of it is that it requires a lot of storage space, especially for large datasets. Partitioning divides the queue into smaller chunks, often by region or by time. This allows for parallel processing and more efficient queries. For example, analyzing sales data separately by region and then combining results speeds up computations significantly. Approximation is used uses sampling or probability methods to estimate rankings. The main advantage is reduced computational cost, but the drawback is slightly loss in accuracy. So, many business applications, an approximate top 10 ranking is good enough for decision making. Benefits of ranking cube is they provide speed by giving instant results, and they maintain accuracy by delivering precise top key answers without scanning the full dataset. Examples include media platforms showing top 10 radios or retailers displaying best-selling items per region. Here we compare sampling cubes and ranking cubes. Sampling cubes focus on efficiency through approximations, while ranking cubes focus on quick computation, orders, results for quick retrieval, both aim to speed up the query process, but suit a different analytical needs. Because the cube technology comes with challenge maintaining accuracy in large dynamic datasets is difficult. Real-time updates can be complex. There are also trade-offs between storage and speed. Solution often involves hybrid system, advanced indexing techniques, or combining sampling with ranking approaches. Looking ahead, cube technology is evolving. We see tighter integration with AI, adaptive sampling, and ranking. Graph cubes to capture complex relationships. Real-time updates with streaming processing applications will expand into IoT analytics, personalized recommendation, and even more dynamic business intelligence. Thank you.